Hello ladies and gentlemen, welcome to Edu-ca-te. Today we're going to be talking about the concept of Maxwell-Boltzmann curves. So I strongly recommend you to watch our previous video on the rates of reaction and the collision theory in order to understand the distribution curves even more. So the Maxwell-Boltzmann distribution curves are actually graphs or curves. We just call them curves because they are graphs. So those curves and graphs show how the energy of the particles that are reacting or of the reactants is distributed. So these curves help us to know how many molecules and particles react successfully, or how many effective collisions we have. Remember, when you say that you have got an effective collision, from our previous video, I'll just give you a recap that when you've got an effective collision, you've got one molecule plus the other molecule bumping into each other or colliding with each other, such that they would do what? They will form a certain product. So this is an effective collision. So if these two bump into each other and form some product, then it is an effective collision. But then if they fail to form some product, it is ineffective. So what makes a collision effective? Remember that they must have they must have the kinetic energy that is enough. Their kinetic energy, the energy of this particle and this particle, must be enough. By enough, it just means it must be greater or equal to the activation energy, which is the minimum energy required for this whole reaction to take place. So the Maxwell-Boltzmann distribution curves have got three labels, which is the number of molecules, the energy that those molecules have, as well as the activation energy of the chemical reaction. So let us look at an example of a Maxwell-Boltzmann curve. So this is an example of a Maxwell-Boltzmann curve. This is the format. Remember, this label is the number of molecules in the y-axis. The number of molecules just tells you how many molecules are reacting, or how many molecules are part of the chemical reaction. So for example, we want to react these molecules. We put 1, 2, 3, 4, 5. So here we are going to write what? We're going to write 5, meaning that there are 5 molecules that are reacting. So it's just the number of reactants, or the number of reacting particles. Then the x-axis shows the energy of those particles. Remember, the energy of the molecules, or the particles rather. So the energy just refers to how much kinetic energy do they have. So maybe this one has got 2 joules of energy, maybe this one has got 3 joules, maybe this one has got 5 joules. I'm just giving an example. So this is the energy that we write here. And then last label is the activation energy for the reaction. So the activation energy is the minimum energy that these molecules are required to have, so that the reaction can successfully take place, or so that the collision can be effective, right? So this is the activation energy. So it means that when the particles reach this activation energy, it means that they will be able to react successfully. So for example, if we say the activation energy for the formation of H2O is maybe the activation energy there is 2 joules. So it means when you are adding hydrogen and oxygen in a balanced chemical reaction to get water, then it means that the energy of hydrogen and oxygen, when you are adding them together, there must be 2 joules or more, so that water can be formed. If they are less than 2 joules, then they won't be able to collide effectively. So that's the whole concept of the activation energy, which is the minimum energy that you are required to have, or the minimum energy that these particles are required to have, so that they can collide effectively. So here you can notice in the graph that many molecules in this reaction have got low kinetic energy. By many molecules, I just mean that the number of molecules is many. So you can see that at the top of the curve here, at this part, this is the maximum number of the molecules. So this is the highest number of the molecules that are present. So here, for example, I've said that there are 5 molecules. So you can see that even if you look any part of the graph, this is the maximum point, or this is the highest number of molecules present. So many molecules have got what? Have got lower kinetic energy. So when you say that we've got a lower kinetic energy, it means that their kinetic energy is below the activation energy, meaning that they cannot react successfully, right? Because you have to meet the minimum energy, which is the activation energy. So you can see that all these particles, all of them, as many as they are here, they cannot react because they are far from the activation energy here. But then if you can see these molecules here at this point, they are equal to the activation energy. They've got their kinetic energy here is equal to the activation energy. Hence, they can react successfully or effectively. So those are effective collisions. So fewer molecules in this reaction have got sufficient kinetic energy. When you say that the kinetic energy is sufficient, it means the energy of the particles is enough for the reaction to take place. Just like here in this example, if hydrogen has got 1 joule and oxygen has also 1 joule of energy, when you add them together, you get 2 joules, of which it is enough for the reaction to take place, right? So here, those particles that have got a kinetic energy that is equal to the activation energy or greater than the activation energy, all of these particles here, all of these particles will react successfully. So this is how you analyze a Maxwell-Boltzmann distribution curves. It is just telling you how the energy of a chemical or of those reacting particles is distributed. So let us look at the curve for temperature. So remember that when you are increasing the temperature, remember that here you're increasing the temperature, you are making the chemical reaction hotter. Yeah, sort of something like you're adding heat. So that's increasing the temperature. So when you increase the temperature, you also increase the kinetic energy of the reacting particles. So for example, in this basin, if you have got particles, let's say this particle had 20 joules, and then you increase the temperature, or you heat it up. Yes, you heat it up, then it means that it will have something like maybe 50 joules. So it means you have increased its kinetic energy. So the whole point of increasing temperature in the reactants, it is increasing their kinetic energy. So it means that when they've got a higher kinetic energy, more of them will be able to react because their kinetic energy must be high so that it can meet the activation energy. So here you can see that this is the dotted curve representing the this is the distribution curve for higher temperature. So this is for higher temperature. So why do I say it is for higher temperature? You can see that in this curve, many molecules at this point, maybe these molecules are 20. So here, 20 molecules here are able to reach the activation energy. Hence, it means that they're able to react effectively. But then if you see when you decrease the temperature, it means less molecules. By less molecules, remember that we look at the y-axis, which is the number of molecules, right? Maybe the molecules here is just 3 molecules. So for a lower temperature, the curve will indicate that less molecules here will do what? Will reach the activation energy. So here, when you're increasing the temperature, you will draw this curve to represent that more molecules will have enough kinetic energy. That is just the collision theory. You're explaining that your increase in temperature is causing these particles to increase their kinetic energy. And when their kinetic energy is high, some of it will meet the activation energy in such a way that a reaction will successfully take place. So when this kinetic energy of particles increases, it means more particles will have enough kinetic energy. When you say that it is enough, it means it is greater or equal to the activation energy. Hence, in the graph with a higher temperature, more particles have enough energy to collide effectively, for an effective collision to take place, for them to form a product. So it means all of these particles that have got an energy that is less than the activation energy, all of these that have got an energy less than the activation energy, they will not be able to react successfully, they will not be able to form products because their activation energy is their kinetic energy is below the activation energy. So this is how we draw the Maxwell-Boltzmann curve for temperature. So when they tell you that you increase the temperature, all you just do is to increase the number of particles that reach the activation energy. So now let's look at the graph or the curve for concentration. So please do not think that concentration is anything complicated, but concentration is basically the amount. It is just counting how many reactants are we having in a given volume or in a given space. So for example, if you can see here, we've got 1, 2, 3. Then we take the very same basin here. Then we put 1, 2, 3, 4, 5, 6, 7, 8. So can you see that here the concentration is low because I've got only 3 molecules per basin, per this volume, per this space. We only have got 3 molecules, but then in this instance we have increased the concentration of the reacting molecules. So according to the collision theory, here let's say maybe this had got 20 joules, then this had got 4 joules, let's say maybe this had got 3 joules, and we say that the activation energy here is what is maybe it's let's just say it is 19 joules. So it means that this one will not be able to react because it has got an energy that is less than the activation energy. But then this one only will be able to react. This one will not be able to react because it has got an energy less than the activation energy. So here only one of them will react. But then here, when you increase the number of particles, it is possible that some of these particles will have enough kinetic energy. So collision theory is just applying here to say that here in this first part of the curve we have got a lower concentration. A lower concentration just means that there are lesser or there are fewer number of particles. Let us say the particles here are what? Let's say 1, 2, 3. Let's just say we've got 3 particles here, and then we decide to increase, just like in this basin, we decide to increase them to what? To 1, 2, 3, 4, 5, 6, 7, 8, to 8 particles. So can you see that we've increased their concentration? So here, when you increase their concentration, the whole point is that when there are more particles, it is possible for many of them to reach their activation energy successfully. So here you can see that more particles are reaching the activation energy and they are able to react effectively. But then if the concentration is low, like at this point, the concentration is low, then it means that there will be a fewer particles that will be able to reach the activation energy. Hence, they won't be able to react effectively. So in the above curve, it is noticeable that the graphs represent 2 different concentrations. So the one above, as I've mentioned, this one has got a higher concentration, whereas the one below, this one has got a lower concentration. So when you increase the concentration or you increase the number of molecules, you just put more reactants, then more particles will have enough or sufficient kinetic energy for the reaction to occur. Then it means there will be more effective collisions per unit time. So that is the whole point. This is how you represent the concentration, the change in concentration. Be it you are increasing it, you are going to draw this curve. If you are decreasing the concentration, you are going to draw this other curve. So this is the Maxwell-Boltzmann distribution curve for concentration. Then the other one which you have, it is the addition of a catalyst. Remember that when you add the catalyst, you want the reaction to be quicker. When you say that the reaction is quicker, it means that there will be more products that are formed in less time. Remember that when something is taking less time to complete, it means it is quick, right? Yeah, when you're taking long to do something, you are slow. When you're taking shorter time to do something, you are quick. So here, when you're adding a catalyst, you want the reaction to be quicker. So it will take less time to complete. So how does the catalyst make the reaction take less time? How does the catalyst increase the rate of the reaction? Remember that the catalyst, it decreases the activation energy. Always it decreases the minimum amount of energy required for the formation of the products, right? Yes, so for example here, if we say that for this reaction to occur, it requires an activation energy of 30 joules. Then we have got here a basin, then we put here hydrogen. Let's just say this is your hydrogen. Then we put here, this is your oxygen. And then this hydrogen has got only this hydrogen has got 20 joules, this oxygen has got 3 joules. So this is the energy of these particles, the kinetic energy of the particles. And then for them to react successfully and form water, or to collide effectively and form water, they need to have a minimum energy of 30 joules. But then if you can notice here, this one has got 20, this one has got 3, so together they've got 23 joules. They will not be able to form water, these two particles, because their kinetic energy is lower than the activation energy. So when you're going to add a catalyst, let's say you add another chemical here, which is your catalyst, which is the chemical that will speed up the reaction. How does it do that? It will decrease this minimum energy required. You just find out that the minimum activation energy required for the formation of water will now be something like 15 joules. So can you see that if the minimum energy is now 15 joules, these two can collide, because this one has got 20, this one has got 3, this will be 23 joules. They will be able to collide effectively and form water. It is because now their kinetic energies are greater or equal to the activation energy. So the whole point here of a catalyst, it decreases the activation energy. So when you are representing that in a Maxwell-Boltzmann curve, you are going to represent that here. Here, when you've got no catalyst, can you see that the activation energy is high at this point? Remember, on the x-axis, as you go from left to right, you are increasing your values. So here, maybe let us just say the activation energy is 20, let's just say it's 30 joules, as our example says there. For water is 30 joules. So here it is 30 joules, and these two are not able to react for this reaction that requires 30 joules. So here, what do you do when you add a catalyst? You decrease the activation energy back there to something like 15 joules. So it means that these two particles will only now require 15 joules so that they can, hence we can say here, more particles will be able to react, or more particles will be able to meet the activation energy, because the activation energy has been reduced. Hence, when you draw the effect of a catalyst, you only shift the activation energy to the left, to say that you have reduced it by adding a catalyst. So in the graph or the curve above, when you add a catalyst, the activation energy will become lower, and if it is lower, then more particles will have sufficient kinetic energy so that they can react, or so that they can collide effectively. And when they collide effectively, boom, we have got a higher reaction rate. I hope that this video was of help to you. Next time we're going to be doing the calculations that are associated with the rates of reaction. Stay tuned for the next video.